Well, let's continue where we left off in the last video. Right. Previously, we have arrived at this step by considering Schrödinger's equation of a magnetic field going through a giant wave function in a superconductor. This equation, which shows that if there is an external magnetic flux going through the wave function, then there must be a current J that circulates in the wave function, which is related to the external flux by this equation. Now let's look at this equation and what it means in more detail. Consider a cylinder . Long cylinder. Suppose that there is a magnetic field, an external field over the cylinder, and suppose that this cylinder is superconducting. So what we know from Meissner's effect is that this field gets expelled from the superconductor, and what we understand from the assumption of a giant wave function is that the external field produces a circulating field in the wave function. So we would expect that this circulating field in the wave function, the circulating current in the wave function, should then produce an opposing magnetic field that cancels the incoming one. And that, of course, means that the field produced by this circulating current has to be equal and opposite to the external field, so that the external field can be completely cancelled within the superconducting body. Now, before we go any further, let's take a step back and think about this current. Now, from the previous result, from this result here, we see that the current is produced when there is a magnetic flux going through the wave function, this giant wave function made up by the electrons in the superconductor. Now, you may have noticed a contradiction here. We need a magnetic field in the superconductor to produce this circulating current, and yet Meissner's effect tells us that the superconductor expels the magnetic field from inside. So if it expels the magnetic field so that there's no field in the body, how can there be a circulating current, since we know that there must be a field to produce that circulating current? Therefore, what this suggests is that not all the magnetic field is expelled. It suggests that there might be some field that remains possibly close to the surface. So whereas most of the external field will get expelled, so that if we sketch field lines around the body. Most of them would be diverted outside the body. There might be just a tiny bit that enters slightly into the surface, so that this bit here, this bit of the magnetic flux would then produce a circulating current according to that equation, and this circulating current around the surface would then produce the required magnetic field that cancels the incoming one. Now this idea of the magnetic flux penetrating a little bit into the surface, say by a certain amount lambda, is called London penetration depth. So some field must still penetrate into the superconductor for this Meissner's effect to happen. Okay. What we're going to do now is to try and derive a formula to estimate this London penetration depth, which I shall call lambda. Now we are going to assume that all of the flux is uniformly enters uniformly into this thin layer of thickness lambda. That of course is not likely to be the case. It's likely to be some kind of a gradation where the field gets weaker and weaker further into the body. But for the purpose of our estimation, we are just going to assume that within a fixed distance lambda into the surface, we have a uniform external field. So this means that if I look at a cross-section of the body, then we can think of this bit of the area. Right, the cross-section is circular. We can think of a thin circular ring of width lambda through which the external field would penetrate, and within the ring there would be no field. And this means that, and this gives us a way to estimate the magnetic flux that goes through the superconductor, because we know that the magnetic flux is equal to magnetic field times area, and in this case the area is just this shaded bit with a thickness of lambda. So this would be approximately now I'm just going to let the circumference of this cross-section be c. So approximately this area would be c times lambda, since lambda is quite narrow. So b and a would be c lambda. That would be the flux. Now from this equation up here, we see that the flux is related to the current density by this formula. Okay. So since we know that the flux is only restricted to this shaded area, we have this expression for the flux in terms of the London penetration depth. So let me substitute this into that expression. no. If I now make B the subject, I'll get B is equal to, right, I would move that over, so that there's a minus sign. I would cancel the C, which is a common factor, and I would get mj on top. I have a q coming down there to give a q squared. I have a rho, and I have a lambda. So I get an expression that relates all these terms here to the external field. Now next, we are going to think about this current density J. Now these currents are supposed to produce a field inside the body that we know is equal and opposite to the external field, so that the field inside the body becomes cancelled and equal to 0. Now actually, given this circulating current, we know how to find the magnetic field that is produced by this circulating current. The formula is just the formula for a solenoid. Now if we think about, let's think about a solenoid that looks like this. Okay, and we think of a current that goes around the solenoid, and that picture there, this curves and the arrow, does not look so different from those arrows there. And if I have a solenoid with a current I going around it, the formula for the magnetic field in the solenoid is mu naught times the number of turns in a coil times the current divided by the length of the solenoid. Now we're going to try and make use of this formula to calculate the field produced by the current density J. So let this length be L, like the solenoid. Now if we think about this current as corresponding to this current density, then we need to consider the whole all of the currents that is going around at the same time, and the total current in fact that goes around the surface of the solenoid, all right, is in fact Ni. Okay, if I think of the total current going through, say, a section of the solenoid, then it would be N times I, because there are N turns. Now in this case, I can think of a corresponding the total current that flows around the surface by considering, say, a cross section of this current sheet that goes around. That would be a section like that, and that would have a length L and a thickness lambda. Okay, so the total current going through this area is just the current density times the area, which is L times the thickness. So in fact, this is the total current here, and Ni is the total current in the solenoid. So these are the corresponding quantities, and therefore we can equate this to the Ni in the solenoid, meaning that this the B produced by this would therefore be mu naught times Ni, which is J L lambda, divided by L. And we see that the L can cancel. Alright, so this term here is the field that we would expect this current density to produce, the opposing field. Okay, now strictly speaking, I should not use the same B as this. That's the B from outside. So this is the B from the current inside. Let me call that B primed. And actually they are different in the sense that the magnitudes are the same, but the directions are opposite, alright, so that they cancel. And in a sense, that's why we have a minus sign here. So in terms of the magnitude, therefore, we see that the magnitude of this external field should be equal to the magnitude of this field from the circulating current. So therefore, we can equate those two expressions. That is equal to mu naught J lambda. Now the purpose of going through all this mathematics is to derive the expression for the London penetration depth, lambda. Now looking at this, you see that we have the common factor of J on the two sides, which we can now cancel. And then we can finally solve for lambda. A lambda there and a lambda there. So let me bring this lambda over to the right and bring the mu naught over there to the bottom on the left. And once we do that, we get lambda squared is equal to m over q squared rho mu naught. So that's our formula for the London's penetration depth. Now from this formula, we can actually estimate a number for lambda for a typical, well, for metal that becomes superconducting. So for example, if we think of niobium, alright, as an example, we can, for example, Google for rho, the number density of electrons. Now we can't Google for it. We might not be able to find the number density directly, but we could find the volume for 1 mole of niobium. Alright, then if there is 1 mole of conduction electrons, we can then find the numbers that density rho, and the m would just be the mass of the electron, q the charge. So therefore, we can actually find all these numbers, and if we go through the calculation, that would give a typical value for the penetration depth of about 300 angstroms. Okay, so that finishes this topic on penetration depth.